population growth continues to increase every day. This results in a higher demand for fuel oil to carry out various activities, especially transportation. This is inversely proportional to petroleum production, which is decreasing due to the aging wells. Petroleum is a non-renewable energy that will run out if used continuously. The process of forming petroleum comes from plant or animal fossils that have settled for millions of years. If there is no other innovation to produce fuel oil, there will be a huge problem.
This increasing population growth will directly affect human waste, especially plastic waste. Plastic is a synthetic polymer material whose compounds and structure are not recognized by microorganisms in soil and water and are difficult to decompose.
On the other hand, biomass potential has yet to be maximally utilized, including Calliandra wood. Calliandra wood is a plant from the Leguminosae family spread in Southeast Asia. Calliandra has fast growth. At the age of 6 months, the height reaches 2.5 until 3.5 meters, and the first year, the height reaches 3 until 5 meters on adequate land. Calliandra has root nodules that can fix nitrogen to maintain soil fertility.
We are introducing Xentaline, a revolutionary product created from discarded plastic waste and bioethanol, combining technological sophistication with environmental concerns, which is not only limited to engine efficiency but also significantly contribute to effort to reduce plastic waste and carbon emissions. How Xentaline is made.
Plastic waste was collected and soaked with 1% disinfectant for 1 hour, then dried in the sun for 24 hours. After that, PET and PP plastics are cut into small pieces for feed into reactor 1, and the thermal cracking process occurs at 400 Celsius with atmospheric pressure. Thermal cracking breaks large hydrocarbon molecules with long carbon atom chains into smaller hydrocarbon molecules by utilizing heat. Furthermore, the cracking product will enter reactor 2, and hydroprocessing or hydrocracking occur with the help of hydrocarbon injection and haloside nanotube catalyst. The reactor output also undergoes a forming process with the help of R34 catalyst to increase the octane value of the product. The resulting product is gas Faza, which is then cooled using a condenser, so the final product is liquid Faza Naphtha.
Sampling of red flower Calliandra wood stem waste raw material. Removal of Calliandra bark waste. Crushing air drying Calliandra bark waste to the smallest possible size with a wood shaving tool with a thickness of about 0.5 mm and length width of 3 mm. Testing the free moisture content and moist moisture content of Calliandra wood stem waste powder. Delinification process of Calliandra wood waste with 2 normality of natrium hydroxide solution, 1 to 5 weeks per volume. Temperature 85 Celsius, stirring at 120 rpm for 5 hours, followed by washing Calliandra wood powder with distilled water until neutral. Hydrolysis process with a 4 normality of sulfuric acid, 1 to 5 weeks per volume. Temperature 30 Celsius, stirring at 120 rpm for 24 hours. In aluminum with flexible rubber lid, followed by filtering the hydrolyzed solution with filter paper. Fermentation of the hydrolyzed solution using 10% of Saccharomyces yeast at 30 Celsius in an incubator for 72 hours. Analyze of bioethanol content from fermentation, calculating the concentration of bioethanol formation in the sample with refractometry at 20 Celsius. Blending is mixing two or more products to obtain the desired result. In this case, blending uses naphtha product produced from the pyrolysis of PET and PP plastic waste and bioethanol from Calliandra wood. This blending is intended to produce B30 biofuel with a composition of 50% naphtha, 30% bioethanol, and 20% toluene. The blending process was carried out at 16 Celsius with 120 RPM stirring.
After blending, the resulting product must be tested to determine the specification to match the fuel requirement. Some of the tests carried out are based on the table below. The blending process occurs between the pyrolyzed naphtha product and the bioethanol product from Calliandra wood. Mixing these two products is to obtain optimal biofuel specification ready to be used as alternative fuels. Based on the test result, it can be concluded that the product of mixing pyrolyzed naphtha and the bioethanol from Calliandra wood can be used as an alternative fuel. In addition, the resulting emissions are also lower than emission of fuel fossil product.
The reactor has a maximum capacity of 5 kg. If 5 kg of feed is processed, the production cost calculation is as follows. This is the raw production cost required to process 5 kg of plastic feed and 1 kg of Calliandra wood. In a day, it is estimated that this process can be done 6 times. The estimated product that can be produced as a pyrolysis naphtha product is 3 until 5 liters per batch. At the same time, the bioethanol product produced is 2 until 3 liters per batch. Therefore, the number of Xentaline product is 5 until 8 liters per batch. The cost-benefit calculation of the Xentaline product is as follows, where the production costs are 13,066 rupiah or $0.83 per liter.
The advantages of Xentaline product are: first, the product produced is of comparable quality to gasoline made from crude oil. Second, if the Xentaline produced on a large scale, it can reduce the need to import crude oil used to manufacture conventional fuel, alleviating the energy crisis. Third, improve combustion efficiency. And the fourth, reduce greenhouse gas emission in the flue gas.
The conclusion of this research, among others: first, Xentaline product can be made with a composition of 50% naphtha, 30% bioethanol, and 20% toluene by blending process at operating condition of 120 RPM and temperature of 16 Celsius. Second, the test result of Xentaline product obtained a density value of 0.765 gram per centimeter cubic, research octane number 98, and rate vapor pressure of 46 kilopascal, which met the specification of commercial fuel. Third, Xentaline products have an affordable price and produce lower carbon emission than conventional fuels. Last, Xentaline products fulfill the 7th point of the SDGs on clean and affordable energy, the 9th point of the SDGs on industry, innovation, and infrastructure, and the 13th point of the SDGs on action climate change.